Okay, so I want to just kind of go through what we talked about in class and then do a couple of these problems that are from your homework so that you have a little bit of kind of context for that. So we talked about this definition of continuity, right? Continuity, this at a point, if the limit, the two-sided limit, is equal to the function value. If the limit as x goes to c of f of x is equal to f of c, that's full continuity. Then we also have a definition of right continuity. If the right limit is equal to the function value, then we say it's right continuous. Same thing for left continuous if the limit from the left is equal to the function value. And then we talked about this second box is the stuff that I did in red. And I had kind of this three-stage test, and we did that for the absolute value function, okay? And then it's like if functions are continuous on a bunch of points in a row, then we can say it's continuous over a closed interval. So, for example, and these are the examples that we did. So, and I've asked you as part of your homework to put this in your library of functions. To write down where we know functions to be continuous. Now, based on kind of this criteria. And so we have, and we talked in class, that, for example, polynomials are continuous. So we'll make continuous functions on minus infinity to infinity. And maybe I'll list all of these. Exponential functions are also continuous on minus infinity to infinity. Let me think. What other ones do we do in class? So we also have I'm going to make these two columns, and maybe I'll just make them simultaneously. So out of trig functions, sine and cosine are continuous everywhere. Right? But then I come over and, for example, rational functions are only continuous on their domain. So which means that, for example, for the function 1 over x, it's discontinuous at x equal to 0, where the function is not defined, right? We also have log functions. Log functions are continuous on their domain. We have, and then some of the trig functions, the other 4 trig functions, again, continuous on the domain. We also talked in class about this absolute value function. It's continuous on minus infinity to infinity. And we didn't talk about these, but odd roots like x to the 1/3 power, things like that, should be continuous on minus infinity to infinity. Right? And then even roots should be continuous on their domain. Now, I'm really saying, so for a lot of these are like base functions, so the square root function is continuous on its domain. And then once you start combining this, it depends on the continuity of the combinations that you have. So that is this second box on the second page that I gave you, right? And it tells us if f and c are continuous functions, then these combinations are also continuous. So f plus c is continuous, f minus c is continuous. I can multiply by a constant multiple. It stays continuous. I can multiply two continuous functions together and the result is continuous. That's this product. Number 4, quotients. I can take the quotient of two continuous functions. The result is continuous wherever g of c does not equal 0. So again, that's going to be a place where the function is undefined, so it doesn't meet the continuity requirements, right? For powers, f to the nth power, where n is a positive integer, is continuous. So as long as f is continuous. And then roots, the nth root of f, if you have kind of an interval containing c and n is a positive integer, then the nth root should also be continuous. Okay. Okay, so we have this, and then we also have continuity of compositions. So here, and I'll remind you, the composition of functions f of g of x or f of g of x, right? Taking one function and plugging it into another function. If I combine two continuous functions, right, and that's this theorem, if f is continuous at c, and g is continuous at f of c, then the composition g of f is continuous also at c, right? So it really is that I have this kind of point that I plug in, c goes into f, and I get f of c. Then f of c goes into g, and so at g, as long as it's continuous at f of c, everything is good and this composition is continuous. Okay? Okay. So I just want to make sure, these are the main things, and we're going to talk about limits of continuous functions. That is not rough, but I kind of want to talk about a couple of the problems that I gave you, and problems from your homework. Okay, so I have some problems here, and what I want you to do is, for this group of problems, and for whatever I signed, and it's right in here, and I'll put in the note for you to follow the instructions in the video. This is what I want you to do. So for each problem, ignore the instructions in the book. A, decompose each given function into several, as many as you need to, component functions. Tell or state, maybe is a probably better, more mathy term, state where the component functions are continuous and discontinuous. Okay? And for B, then I want you to write y as a combination of these component functions. And then part C, I want you to answer the real question, like where is y continuous and discontinuous? State which properties from theorems, I think it's 8 and 9, you used to arrive at your conclusions. So I just want to see you break down these functions, and so you're able to use what we know about this group of functions, these continuous functions here, right, in these problems. So I'll show you what that looks like, but I want to break it down into component functions. So let's do a couple problems. Let me see out of your book. So let's do problem 13, right? So problem 13, y is equal to 1 over x minus 2 minus 3x. Okay, so for each of these, you're going to have parts A, B, and C. So A is this decomposition. So I just see two functions here. This is a rational function. I know rational functions were in the list above and are continuous everywhere they're defined. And here's a polynomial function. So I'm just going to give those names. F is 1 over x minus 2, and G is 3x. This is continuous where it's defined, and discontinuous at x is equal to 2. This g of x is continuous everywhere. Okay, now, then if that's true, y is f minus g. So this is rewriting y as this component functions. And then c is, where is y continuous? So y is continuous at every point where both of these are continuous. So here y is continuous from minus infinity to 2 and 2 to infinity. And it's discontinuous at x is equal to 2. Okay, and which property? The property I used here, it's a simple one. It should just be the difference property. From Theorem 8. Okay, I'm going to do a little bit more complicated one. But you can only use what we know from that list above, so you can't just kind of make statements about things being continuous. So let's say I want to look at 17, and I want to look at y is equal to the absolute value of x minus 1 plus sine x. Right? Okay. Okay, so now I know that the absolute value function, absolute value of x, is continuous. And what I have here is a composition of the function x minus 1 and the absolute value. So I could name, like maybe a first try would be to name f is absolute value of x minus 1. But really I don't have a general statement about all absolute value functions, so I need to use the composition here. So I really want to let f be absolute value of x. I think, let's say g is x minus 1 and h is sine x. Right? Then for part, what do I know about continuity? This is continuous everywhere. Oh, these are nice. This is continuous everywhere. And this is continuous everywhere. Okay? Now, for part B, this is all A. For part B, y is f of g of x plus sine x. Do you remember when we did these compositions and broke them down when we did compositions of functions? Okay. And then the two theorems that I have, C, this means, oh, whoops, this should be h of x, right? Instead of sine x. Okay, good. So now I'm going to use the composition theorem, which I think is theorem 9. Is that right? Yep, compositions of continuous functions. So y is continuous everywhere. And I used the composition property. And also this right here, I'm adding two functions together. So also the sum property. Or addition property. I don't know which one it's called in your book. Oh, sums. Look, sums. Okay. Yeah, I think maybe that's what I want to say. So I'll give you a few and try and decompose them and write these, but do parts A, B, and C for the ones that I assign. And just let me know if you have questions. I think a lot of these will feel real similar to when you were listing properties for limits. So that should come in handy.